Well, greetings, mathletes, and welcome back. We're going to be talking about the chain rule today, and we're going to have two different presentations of the chain rule. The first presentation definitely works. Sometimes it takes a little bit longer, but it's a little easier to see what's going on because sometimes there's a lot of moving parts to this stuff. So the first way is good for that, and it's also good for the next two sections that we're going to be covering when we're talking about implicit differentiation and related rates. Both of those use the chain rule in its first form. So we will be looking at that first. And then the second way to look at it is, well, it's a little nicer if all you're trying to do is take a derivative and there's not a bigger problem to deal with. It's nicer to use the second form of the chain rule. So we actually have two different ways to take a look at this. And, well, let's just get started and take a look at those two different ways. Okay, so I'm going to make two different statements of the chain rule here. Let's actually get this down a little farther. There we go. The chain rule. Oftentimes this is looked at as a way to relate two variables using a third variable. And that's the first form that we're looking at. So what we're saying is if I want a derivative of y with respect to x, one of the things I can do is look at a third variable, u, and I can relate y to x using this third variable, right? And you notice, and the third variable in this case is u. So dy du times du dx. So it's the change in y with respect to u times the change in u with respect to x. And you notice they look like fractions, and you have this feel, and I'm going to write this in, although technically, I don't know, I don't think technically it really works like that, but if you kind of treat them like fractions, you can see how this kind of connects together, right? You can kind of see that du cancels out and you're left with a dy dx. This is one of those places where it is okay to think of it as a fraction. That is not always the case. Okay, so that's the first statement of the chain rule. The second statement of the chain rule has more to do when you're looking at a composition of functions, right? And this technically is a composition of functions, but it's a little easier to see when you look at it this way. Oops, let's switch that back to blue. So if I have two functions, f composed with g of x, and I'm looking for their derivative, right? What I can do is I can take the, well, let me rewrite it this way first so we can see it, right? And what I'm looking for is the derivative of that whole business, right? Whatever that composition of functions is. What I do is I take the derivative of the outside function without touching the inside function, and I multiply that by the derivative of the inside function, right? Now, this is all very technical right now, but let's actually see how this plays out. So we're going to start with this first statement here, right? Finding dy dx when we have something else. Okay, so let me go ahead and clean this off, and we'll take a look at a first example here. So let's say I have a function y equal to cosine u, and I have a function u equal to x cubed. Now, notice what's happening here is that since u is x cubed, I could rewrite this whole thing as y equals cosine x cubed. And later on, this is actually what we're going to be starting with, and you have to be able to see the x cubed as the u function, as the inside function. Okay, but for right now, we're starting with these separate. Okay, so let's look at a statement here. If we're going to look for dy dx, what I can do is look at dy du and multiply that by du dx. So all we really have to do is find dy du, right? And that's taking the derivative of this. And I'm going to multiply that by the derivative of this, right? And we're going to see what happens. Okay, so let's see. So dy du, the derivative of cosine is negative sine. So this is dy du is negative sine u. Right? That's one of our trig integrals. Or not an integral. We're not talking about integrals yet. Trig derivatives. Okay, so that's dy du. And then now I need du dx. And if I take the derivative of this, it's 3x squared. So let's put these together because it says we're supposed to multiply this times this. So let's do it. So dy du times du dx is negative sine u times 3x squared. Now, you wouldn't leave the u in there because what I'm looking for is dy dx. Right? I'm looking for dy dx. That means I need to have everything in terms of x's. Well, I already know u is equal to x cubed. So this is now negative sine of x cubed. Oh, actually, let's rewrite it this way. I want to put that 3x squared first. So that I take the negative, it would be negative 3x squared times sine of u, and since u is x cubed, this is sine of x cubed, right? The applications for this actually have a lot to do with, they usually end up with formulas, right? Formulas that describe how a volume changes, and then maybe how a concentration of a gas changes with respect to the volume, and you're trying to figure out how the gas changes with respect to the radius, or something like that. So you would end up relating two different things and then multiplying them together. But the bottom line is, you know, the first problems you guys are going to get look a lot like these, where you're given y of u and u of x as two different functions, and you have to use the chain rule here. This will actually make a lot more sense. This will make implicit differentiation make a lot more sense when we get to that. Okay, so let's look at another example. All right, so let's say I have y is equal to 6u minus 9, and u is equal to 1/2 x to the fourth. Okay, so if we're looking for dy dx, which is what you're going to be asked for, this is going to be dy du times du dx. So I need dy du first. So I can just look at this and find it, right? The derivative of 6u with respect to u would just be 6. Derivative of negative 9 is 0, so that goes away. And then over here, the derivative of 1/2 x to the fourth, I would bring the 4 down. Half of 4 is 2, so that would be times 2x to the third, right? And I just need to simplify this now. This 6 doesn't have a variable in there, so in this case, we don't have to substitute anything back in. So this is just 12x cubed, right? And that's how those things relate. And you notice, I just want to point out something else. If I put this together, right, if I substituted this 1/2 x to the fourth in for u, I'd get y is equal to 6 times 1/2 x to the fourth minus 9. And if I just simplified that, I'd get y is equal to 3x to the fourth minus 9. Okay, now I'm doing this because I want to point out that the chain rule is not always the fastest way to get things done. But I want you to go through these exercises anyways, even though there are often faster ways to do it. From here, if I just take the derivative with respect to x, dy dx, well, the first term, let's see, 4 times 3 is 12, and that would make it x to the third, and the derivative of negative 9 is 0. And so you can see we get the same answer either way. So this is just one more technique is what this actually is. You do need to practice it because it comes up. There are times when it is way too painful to do it another way. The chain rule saves you a ton of time. So, okay, so let's go ahead and look at the next example here. Okay, So let's say I have, yeah, let's do that. So y, that is not a brush. Let's try it again. So let's say we have y is equal to u to the fourth, and u is equal to sine x. Okay, so if we're going to find this derivative, dy dx, it's dy du times du dx, right? So we just have to take the derivative of both of these things. Dy du would be 4u to the third, and du dx would be cosine x, right? Well, u is equal to sine x, so this is actually 4 times sine to the third x times cosine x, right? And that's my dy dx. So you got to substitute that. You have to substitute whatever u is back in. So don't forget to do that. But it's kind of interesting that you can find these kinds of derivatives. I do want to point out that if I composed these two, right, if I actually substituted sine in for u, this would be sine to the fourth times u. And I just want to remind everybody, well, first of all, this would be very painful to not use the chain rule with, because what you would have to do is separate it out into 4 sines separately and use the product rule over and over and over again. And it would actually get really, really cumbersome if we did it that way. The other thing, I want to make sure that we understand this notation. When I put an exponent on the sign before the variable like this, what that actually means, oh, that should be sine x, huh? Yeah, sorry, sine x. What that is sine x to the fourth is what that actually means. So sometimes, especially when we get to the next part of this, it's a little easier to see what the composition is if you rewrite it this way, right? So it just makes it easier to see what the shells of functions are as you go through this. Okay, so let's take a look at one more of these in this form. So let's say we have, let's try this again. Let's say we have y equals 2u to the third, and u is equal to tangent x. Okay, so I want you to see if you can do this one on your own. So go ahead and pause this. Hopefully you've tried a couple of the others on your own too. I forgot to mention that you should probably pause it and try. But see what you can do with this. We know the derivative of tangent. We can take derivatives and all this stuff. See if you can use the chain rule to come up with dy dx. Right? Okay, so I'm going to assume you've paused it at this point. So we need a dy du, and we need a du dx. Right? Those are the two things we need. And so basically what this is y prime and u prime is basically what we're looking at. So let's see. So the derivative of y would be 6u squared. And the derivative of u with respect to x, the derivative of tangent is secant squared. So this is times secant squared x. And so now all we have to do is plug in, we just need to substitute our u in so we can have everything in terms of x. And so dy dx is now equal to 6 times tangent squared x times secant squared x, right? And we have our derivative now. Good, clean fun. So hopefully you got that, right? And notice that it's just a matter of remembering that the derivative of tangent is secant squared. It's a good idea to remember these. I can remember as a student, I didn't want to memorize them. And so what I ended up doing was re-deriving them every single time. I would rewrite tangent is sine over cosine, and I would go through the whole thing every time. And there's nothing wrong with that because it does really reinforce where everything comes from. But you really want to have it memorized at some point. Don't take my example because I wasn't a very good student at that point. It took me a while to figure out what it took to be a good student. So, in any case, that is how we handle it using the first form, right? We're always looking. We're basically always looking for something to relate x to y, and a lot of the time that's an in-between variable. So at this point, we're given this stuff, but in the next two sections, we'll be having to find it. So that always changes things a bit. All right, so let's look at the other form of the chain rule. Okay, so as I said earlier, this second form is more practical, just, well, on the go, so to speak, right? If you're given a function and you need to take its derivative and you can see the composition that it has, you can save yourself a lot of time. So this would be f prime of g of x times g prime of x. Right, and if g of x, I just want to point out how this relates to the other function, or to the other presentation. If g of x is equal to u, then g prime is du dx, right? And you notice here, this is f prime of u, which means that this is, yeah, that's du. I wrote du. I thought I wrote y there for a second. I was like, man. Okay, so what that means is this is our dy du, right? And so that's really what's happening here. That's the connection between these two things. And it's just this substitution that turns one rule into the other. But because it's presented in a different way like this, it's actually easier to use. So let's see if we can do this without making our substitutions, and we can just see what's going on. Okay, so let's take a look at this first. So let's say we have a function, right? And normally this is presented as a single function here, right? And you have to be able to see that it's a composition. So let's look at this as our function. So let's say h of x is equal to 2 times tangent cubed x. Okay, so it might be useful, if you can see it, you don't need to write this, but it may be useful to look at it this way. Right, and so you can see tangent x is the inside function. Right, so first of all, I'm going to take the derivative of the outside without touching the inside function. So I'm just basically treating the inside function is your u, so you're leaving it alone for a moment. So the derivative of the outside would be 3, I'm going to bring the 3 out front, so that would make it 6 times tangent x squared. And I'll rewrite that so it looks nice in a minute. Okay, so that's the derivative of the outside function. The derivative of the inside function would be the derivative of tangent. And the derivative of tangent is secant squared. Right? And so if we just simplify this, we end up with 6 tangent squared x secant squared x. Now, I do want to point out that this is the same as the last problem we did, right? Where we looked at where y was equal to 2x to the third and u was equal to tangent x. Right? It's the same setup basically, and that's why we got the same answer when we worked it out. So that's one of those things where if you can see it, it moves a lot faster this way. So it's a good idea to practice seeing it this way. If you can't see it, it's okay to separate out the u and make it look like one of the previous problems, right? One of the ones where we have a dy du and a du dx. So it's up to you how you want to handle it. I find this to be the most practical way to get a hold of things. Okay, so let's take a look at another one here. Okay, so let's say I have f of x is equal to 1 over sine x times cosine x to the third. Okay, so there's some stuff we can do. If we're looking... That is annoying. I don't know where that came from, but okay. Pretend you didn't see that. Okay, now, one of the things, if you're looking for f prime of x here, whenever I have powers of things in the denominator, it is much easier to use the power rule to deal with these things than it is to use the quotient rule. So that's how I'm going to do it. So I'm going to rewrite this now as sine x times cosine x to the negative 3. Okay. So what we want to do then is we have an inside, and I'm going to call this piece the inside, right? Sine times cosine. And then we have an outside piece, which would be just basically the whole something to the negative third is the outside piece. So the derivative of the outside would be just to bring down the negative 3 and reduce the power by 1. Oops. There. So that's what we're going to do. We'll bring down the negative 3. So I have negative 3 times sine x times cosine x to the negative 4th, right? We're reducing it by 1. That means it becomes more negative. Okay, so that's the derivative of the outside. Now the derivative of the inside might be a little bit more work because I need to find d dx of sine x times cosine x. Right? That's the inside piece. So I'm going to work that out and see what we can get, and then I'll put it all back together. So this is a product, so that means I'm going to use the product rule. So it's 1d2, so that makes it sine x times negative sine x. 1d2 plus 2d1, so that would make it cosine times cosine. Right, and so that gives me cosine squared x minus sine squared x. Okay, so that's the derivative of the outside. Okay, so let's see what we get here. So let's put it all together. So I have negative 3 times sine x cosine x to the negative 4th times cosine squared x minus sine squared x. All right, well, let's clean that up too, because I don't want to deal with the negative exponent. So I'm going to take this term and drop it to the bottom. And I should get negative 3, because that'll stay on top, times cosine squared x minus sine squared x over, let's see, sine x cosine x all raised to the 4th power. Right, so some of these get a little bit messy. And you notice here I had to step out and do a little scratch work to figure out what that derivative of the inside was. Don't be afraid to work things out in a separate space. Right, it actually makes things a lot neater in the long run. I know I'm probably not the best example of neatness when working things out, but it's only because I don't have more space. So, yeah, so it was the derivative of the outside times the derivative of the inside. You just have to kind of be able to peel the layers off as you go. I do want to point out some teachers teach it the derivative of the inside times the derivative of the outside. It's the same thing, right? It's just different ways of looking at the exact same thing. I like to work my way in through the layers. Some people like to work their way out through the layers. There's no real difference either way. Okay, so let's look at another example here. All right, so let's say this is our function. So f of x is equal to cosine of x to the 5th over x plus 1. Okay, so we want to find f prime of x. All right, why don't you pause it here and see if you can find f prime of x? I think that would be a good exercise. This is getting to the point where we're stretching the edges of what's going to be asked of you in the homework and on exams and things like that. So let's see if you can do it by yourself. So go ahead and pause it here, and then we'll see what we can get. Okay, so looking at this, I think we can see what the inside function would be this piece right here, and the outside function would be cosine. So if I start with the derivative of the outside, it's just dealing with the cosine, which would make it negative sine of x to the fifth over x plus 1. Right, so that's the first factor in here. Now the second factor, I need the derivative of this inside piece. So I know that's going to get multiplied by whatever's next here. I need to be able to take that derivative. So let's see what we can do here. I'm just going to kind of do it on the fly. So d dx of x to the fifth over x plus 1. Let's see, it's low. I'm going to end up moving a few of these things around so I can see it, but okay. So low d high, and the derivative of the top would be 5x to the fourth, minus high d low, which is just 1, over the square of what's below. Okay, so let's clean this thing up and see what we got here. So let's see here. If I just distribute that, that gives me 5x to the fifth plus 5x to the fourth minus x to the fifth. Okay, so that means it's 4x to the fifth plus 5x to the fourth over x plus 1 squared. Okay, so that's the derivative of the inside. So I'm going to rewrite this piece because it's... actually, can I do this? Let's see if I can actually grab this. Hey, I can. I'm going to scoot it over. Okay, and I just need to write... Try this again. I just need to write this piece in there. So this is now times 4x to the fifth plus 5x to the fourth over x plus 1 squared, right? And that's being multiplied. So I actually want to clean this up because this is an awkward way to write this. So I'm going to do this. I'm going to say this is now 4x to the fifth. Yeah, that's plus. Okay. Plus 5x to the fourth times the sine. Oh, and I'm going to put that negative out front so I don't forget it. The sine of x to the fifth over x plus 1 divided by x plus 1 squared. Yeah, there we go, x plus 1 squared. And there's different ways to write it. You could also write it this way, negative 4x to the fifth plus 5x to the fourth over x plus 1 squared times the sine of x to the fifth over x plus 1, right? And that way you can see the derivative of the insides here, the derivative of the outsides here. So there are different ways to write this answer correctly. I just wanted to point that out because there really are a lot of ways to do it. Okay, now I want to look at one more example, and that'll be our last example because that'll pretty much take care of most of the situations we're going to encounter here. And again, this one will be for you guys to play with. So f of x is equal to the square root of sine x over x squared plus 4. Okay, so let's see what you can do with this one. So go ahead and pause it here and then take a good crack at it. Might take you a few minutes here, maybe longer, I don't know, depends what you see. Okay, so if we're going to attack this, well, first thing with roots, I like to deal with the exponents, not with a square root. Okay, so I'm going to look at this whole thing this way. Sine x over x squared plus 4, right? And I'm going to raise it to the 1/2 power. It's just easier to use a power rule when you're dealing with this. So the derivative of the outside, if I want f prime, is just the power function, right? It's u to the 1/2. And if I do that, what I end up with is 1 over 2 times whatever I was taking the root of. Okay, and that looks a little bit messy, but that's okay. Now we need the derivative of the inside piece, and that's this sine x over x squared plus 4. So I'm going to step to the side and do that one. Or x squared plus 4. I think I forgot to say the square. Okay, and that's a quotient rule. So all we have to do is take derivatives of tops and bottoms and follow the rules, basically. So it'd be low d high, derivative of sine is cosine, minus high d low, and that would be 2x, over the square of what's below. Right? You notice I haven't been squaring out what's below. There's no reason you have to unless there's a reason to do it. Otherwise, it's just taking more steps, and every step you take is another place you might make a mistake. So don't do it unless you need to. Okay, so let's see what we got up here. Looks like we have x squared. Let's see. Yeah. So we got x squared plus... Actually, let's do it this way. Let's just put it over here. So we got x squared plus 4x, or x squared plus 4. There we go. I knew I could say it right. Times cosine x, right? Minus 2x sine x. And that's over x squared plus 4 squared. Now, even though we haven't cleaned any of this up or anything like that, this is actually a perfectly fine answer. There are some things we're going to be able to clean up a little bit, though, when we do this. So first of all, I think we can see that the numerator is just that's going to be the numerator of our final answer, right? Which is x squared plus 4 cosine x minus 2x sine x. Right? That's just taking the numerator and multiplying it straight across. Now, multiplying the denominator, I have an x squared plus 4. I have an extra one of those. So I can cancel one of those out. Right? And so what that leaves me with is 2 times sine x times... Actually, let's put it in a different order. Well, that's... yeah. Times this x squared plus 4 times sine x. Okay, now, there will be a very strong temptation to do this, right? You cannot do that. That is an illegal move, and it's because you don't have an x plus 4 in this last term. It has to be present in all of the terms to be able to cancel it out. If it's not, you can't do anything with it. Right? That's it. It has to be in all of the terms. So this would be your final answer, right? We've reduced what we could, and there's not much else we can do other than just changing the way it looks. You might want to, I don't know, you may want to distribute this out or distribute the cosine across the x squared plus 4 or something, but other than those kinds of things, there's nothing else to improve on this answer, right? We've already canceled out the extra term, the extra factor we had. So there's really not much else to do here. Okay. All right. So that pretty much wraps up this particular tool. Okay. So we have learned all the tools so far that we're going to need for derivatives, right? Everything else we're going to learn, all these techniques that we're going to learn in the rest of this chapter, are just applying those tools in different ways, right? And learning how they can fit together in ways that might be unexpected. Maybe they're not unexpected. It just depends on, how your particular brain works. But as far as the tools go, we're not going to learn any new tools. So we have the main things. We have all those rules of differentiation. We have, you can pull a constant through. We have rules about what you do to take the derivative of a sum or a difference. We have the product rule. We have the quotient rule. We have the power rule. And now we have the chain rule. And the chain rule is that's kind of the nail in the coffin, so to speak. That's the end of the line as far as the tools go. Now it's a matter of how to use those tools. Okay, so in any case, until next time, keep your pencils and your wits sharp.